Hello. Good. Well, hi everyone. Welcome to the stream. Let me get the dashboard on my second screen from Twitch, and we are good to go. Okay, there it is. Also, I should post on Discord that I'm streaming. Finished triangle. Now adding vertex buffers on Vulkan. And I'm not sure what is my stream. Oh, it does not appear. What? Is it unlisted? Yeah, it is unlisted. Oh, oops. Okay, there we go now. Yeah. All right. Okay, let's get started. I don't even know where I left this off, so let's build it. Normal triangle. And I already finished all of this, right? Yeah. I mean, let's try this. So, which are the colors? This, and then that's it. Okay, good. We have dynamic data. We're drawing by the size of that. Okay, so next thing, staging buffer. Hello. Yeah, get a window manager on Windows. I was getting tired of having so many tabs and having to alt-tab through all of them to find the one that I wanted to be, so I ended up actually using a window manager. It's a bit buggy sometimes, but when developing it's fine. The vertex buffer we have right now works correctly, but the memory type that allows us to access it from the CPU may not be most optimal memory type for the graphics card itself to read from. The most optimal memory has the BK memory property device local bit flag and is usually not accessible by the CPU on dedicated graphics cards. In this chapter we're going to create two vertex buffers, one staging buffer in CPU accessible memory to upload the data from the vertex array to, and the final buffer in device local memory. We'll then use a copy command to move the data from the staging buffer to the actual vertex buffer. Makes sense. So right now we're allocating with type BK property host visible bit, right? And they are saying device local bit, right? That's the problem. Property device local. So the only way for this to be faster is uploading to the GPU memory directly. Transfer operations, which is indicated using Q transfer bit. The good news is that any queue with BKQ graphics bit or BKQ compute bit capabilities already implicitly supports operations. And we're already checking that, so it's fine. To explicitly list in QFlex in those cases. If you like a challenge, then you can still try to use a different queue family specifically for transfer operations. It will require you to make the following modifications to your program. Modify queue family indices. Yeah, you would have to, instead of present family, you would have, I'll do it just for exercise. What do we name it? Wait, what? Transfer family. And then same thing. Oh, it's so cold. And then here we would basically check indices transfer family assigned. I'm thinking you can just do this. Q flag is BKQ. Oh god. Transfer bit. Does it contain it? How do I know? Yeah. BKQ flag bit, it's in there. And then you would do what is this? Transfer family and assigned. And there you go. Hello Toza. I looked into dynamic rendering and I'm thinking I'm moving what I have to it, but I don't know if it's worth it. It's like 20, well, I don't know if 20, like 40 lines of code less. Yeah, create a second command pool for command buffers that are submitted to the transfer family, change sharing mode. Yeah. Anyways, I'm not gonna do that. But I get it. For now, yeah, for now. I mean, I'm thinking on abstracting a bunch of this because I want to support OpenGL and Vulkan because I want to do a video on benchmarking both in a few scenes. Maybe when I do that, it depends, for example, on the third rendering. Yeah, I mean, maybe in that case. Hello, Ansh. Anyways, I also was trying to use BMA for this, but it's not supported in C. I thought it was. It's only C++. Find the memory type, yeah. Anyways, this didn't change anything, right? Okay. Yeah, I'm also doing the same tutorial and I see someone is also doing the same journey. Hey, good to see hardworking people here. You changed colors? Yeah. It's a good idea to move buffer creation to a helper function. Create a new function, create buffer, and move the code into create vertex buffer except mapping to it. So what changes? Right. BK sharing mode exclusive. Okay, let's see what if this applies. What is it with buffer? Yeah, I don't think it's... But I have to allocate on there anyways, right? Yeah. Then why doesn't it take it? Alright. Well. By the way, have you seen Travis Ruman YouTube channel is making a game engine from scratch using Vulkan? Yeah, I've seen it. He has been working on it for a really long time. I never really saw what he's doing on the engine. But yeah, I think it was called... I forgot. Something related to coffee in another language. Talking about that, I'm drinking coffee. You need more power. Definitely more power. Oh, I'm stupid, right. I mean, I don't need a buffer because they are buffers by default. This is what I don't like about the types in Vulkan, right? If you look under the hood, well, it doesn't show it directly, but you see that there's a type that has a pointer directly, so you don't need to add the pointer. I always forget this. Now, what happened to buffer memory? This takes BK buffer, right? We have BK buffer, and there it takes a pointer and they, okay, whatever, you know, this is too confusing. Should probably sort this. Okay. I got stuck at episode 32 because I don't really understand what he's doing, so I go back to the basics and learn. Yeah, I mean, learning from YouTube tutorials, especially graphics programming, is not the best. I also got lost in the way when I was learning OpenGL. Reading resources are usually top-notch. Because Vulkan finds functions like OpenGL, you need to manually find them. Vulkan already provides it when you load instances, I think. I don't understand. Because those are the types already, right? Why is there a need to add the pointer? For example, where is this? Right, this creates a buffer. You send the buffer info, and of course buffer info doesn't have a pointer, they declare it normally, right? But then when it comes to, for example, create buffer, right, it has this weird type. What is this? Okay, it's directly this. And I'm guessing this is like the type you give it, I'm not sure. Right, so object is what you give it. So in this case, bk buffer becomes bk buffer underscore t and the pointer to the object, but I'm not sure why is this necessary. You said it before, because it points to memory function, create info struct, buffer is pointer to object from system function, something like that, right? I mean, they could still just do that. This has nothing to do with it, I'm pretty sure. This just auto-generates the types. Anyways. So after that, this becomes this. BI maybe I should keep what I had before. Buffer size, where is it? I just close it here. Right, because I just did this. Or I can just get the size of them. Directly, no? Yeah. And this should be, oh yeah. Well, I'll keep it like this anyways, because size T is already unsigned long. Oh. Auto gets from them part of my C++ code. Yeah, right, I've seen that type of code. I manually get this function with this. I do it with the same thing pretty much here. I mean, I'm guessing this is like the same way you would do it on OpenGL. Well, similar. You just need the pointer to the functions. Right. And this one is not available because it is an extension. Run this program and make sure whatever. So what did I do? BK memory is no handle. BK map memory on here. Maybe I do need to pass by, I don't know. Let's try. Is that it? Yeah. What are you doing?
I have to draw my funnels.
Subchain is also an extension, but you don't need to do this way since Vulkan auto loads it for you. Yeah. Did you forget to initialize a value somewhere? No, it was just the pointers. We're going to change create vertex buffer to only use a host visible buffer as temporary buffer and use a device local one as actual vertex buffer. Right, so host one instead of the one on CPU. So it adds host visible bit, host Now there you go. I'm gonna go by CPU plus GPU, yeah. See you later, Toza. Device local is the GPU, right? We are now using a new staging buffer with staging buffer memory for mapping and copying the vertex data. In this chapter, we're going to use two new buffer usage flags. Hello, Igor Laptev. BK buffer usage transfer SRC bit. Buffer can be used as source in memory transfer operations. BK buffer transfer destination bit. Buffer can be used as destination in the memory transfer operation. Okay. From a memory type that is device local, which generally means that we are not able to use BK map memory. However, we can copy the data from staging buffer, right, to vertex buffer. We have to indicate that we intend to do that by specifying the transfer source flag for the staging buffer and the transfer destination for vertex buffer along with the vertex buffer usage flag. We're now going to write a function to copy the contents from one buffer to another called copy buffer. This is interesting. I wonder what Vulkan functions we're gonna use. I'm wondering if... By the way, how long did it take you to reach this point of the tutorial? I'm not sure. I think my triangle speedrun was like 6 or 7 hours, and this point a bit more because I revised everything after doing that. So like maybe 10 hours in or around that. There was a lot of refactoring as well. Oh, you're fast, but I've done Vulkan before and I've done OpenGL before and I'm familiar with a lot of graphics programming concepts and done a lot of C as well. Can't compare it if you're just starting out. Remember, never compare yourself to others, just to yourself from the past. It doesn't help on anything. Memory transfer operations are executed using command buffers, just like, oh, interesting. Therefore, we must first allocate a temporary command buffer. You may wish to create a separate command pool for this kinds of short-lived buffers, because implementation may be able to apply memory allocation optimizations. I could. You should use the bk command pool create transient bit flag during command pool generation in that case. This is for the optimization. That's the allocate info. Comparison is the thief of joy. You're right. Yeah. Pretty much. You get nothing by it, and if you did better, you feel nothing, and if you did worse, you feel worse. Command buffer lower primary, command pool, and that. And immediately start recording the command buffer. I like this pattern, it feels kinda immediate. It's like you begin and then you do your operations inside and then you end. We're going to use the command buffer once and wait with returning from the function until the copy operation has finished executing. It's good practice to tell the driver about our intent using big buffer usage one time submit bit. Okay. These two are optional. Contents of buffers are transferred using the bk command, copy buffer command. It takes the source and the destination buffers as arguments and an array of regions to copy. Content buffer, source buffer, destination buffer, it's like main copy, but in the GPU. The regions are defined in bk buffer copy structs and consist of a source buffer offset, destination buffer offset and size. We don't have offset, but of course size. It is not possible to specify bk whole size here, unlike the bk map memory command. And then you and this command buffer only contains the copy command. Yeah, so we have to execute it. So we can stop recording right now and now execute the command buffer to complete the transfer. And you wait idle on the graphics queue. Makes sense. Actually, now that I think about it, where is the size? I swear I have something for it. Yeah, recreate swap chain, and then we wait unminimized, and then we wait idle. But can you wait on family? Wait on queue? How was it? Wait idle, graphics queue. Oh, like that. BKQ, right? CTQ. Yeah, that's what I wanted to do before. Let's see if it... I mean, it's gonna break because I'm doing whatever. Check. Check it does not break. So create buffer, copy buffer, and here we left it off. I mean, I think that should work because here, I mean, apart from the presentation, I think we can just wait on the graphics queue. Maybe we need to wait on the graphics queue and present queue. I don't know. I'll see. If the validation layer tells me something. Unlike draw comments, there's no events we need to wait on this time. We just want to execute the transfer on the buffers immediately. There are two possible ways to wait on this transfer to complete. We could use fence and wait for fences, or simply wait for the transfer queue to complete idle with queue wait idle. A fence would allow you to schedule multiple transfers simultaneously and wait for all of them complete instead of executing one at a time. That may give the driver more opportunities to optimize. Well, if we end up submitting a lot of memory for vertex buffers, then I mean it's a bit difficult, right? Because what would it be? Copy buffers? I'm not sure. What is breaking the? Oh, this my. Don't forget to clean up the command buffer used for the transfer variation. We can now call copy buffer from create vertex buffer function to move the vertex data to the device local buffer. So right after this, copy buffer, and what do we have to give? Source buffer, which would be staging buffer. Destination buffer. I'm not sure what is destination buffer. Oh, a staging buffer, vertex buffer, right? Render dot vertex buffer and buffer size. And then we can remove this. Well, that's pretty cool. Run your program. Destination is bk null handle. Okay, so that is already at copy buffer, which is copy buffer. This normally nothing happens, right? That still happens. So what was it? Source staging buffer, vertex buffer, buffer size, and something is failing here, I'm guessing. I'm not initializing something. Conclusion, it should be noted that in real-world applications you're not supposed to actually call bkallocate memory for every individual buffer. The maximum buffer of simultaneous memory allocations is limited by physical device limit, which may be as low as high-end software hardware like a 1080. The right way to allocate memory for a large number of objects at the same time is to create a custom allocator that splits up a single allocation amongst many different objects with the offset parameters that we have seen in many functions. Right? That's why BMA allocators were. You can either implement such an allocator yourself or use BMA, provided by the GPU Open Initiative. However, in this tutorial, it's okay to separate the allocations for every resource because we won't come close to hitting any of these limits now. Yeah, I mean, 496 for a triangle, it's fine. But I'm having trouble debugging my code. I'm trying to create a separate transfer queue family. I'm not doing that. My code differs from the example by class name. What? You state using staging buffer that using a fence instead of bk wait idle would allow you to schedule multiple transfers. The documentation for, however, states having submitted a valid fence. Okay, I mean, it could be true. I don't see why wouldn't this be the case, right? Because that's async anyways, and you have to wait until the GPU stops working. So the logic applies, I feel. By the way, just gonna bot comment band. Best viewers on whatever site. Maybe I did something stupid, so oh, what? Let me just look at the code instead. So we are on create buffer. Right. When creating the vertex buffer, they create it twice. First they use staging buffer and then they create the vertex buffer memory. And that's what we were failing on, right? We need to create the staging buffer where we allocate our stuff on CPU and then create the second buffer. So create buffer, then this. Hey, thanks for the follow, JMux. So we do that and then they create the second one. So this is source, this is destination. Yeah, that was the problem. Usage vertex buffer bit, and this is host coherent bit. BK property device local bit. Vertex buffer. Wait, we don't have vertex buffer memory, or do we? Oh, yeah, we do. What is that emoji? Peppo happy. So create buffer, copy buffer. And then we destroy here, right? Wait, free memory, free buffers. Yeah. So create buffer, copy buffer, and this. I was getting confused. Render, no, render, no. Let's see. There you go. And now if I resize, yeah, it looks good. So let me look through it again. We create our staging buffer. Create the memory and get the size from the vertices, which are here. We create buffer with usage transfer SRC bit. Buffer usage flags, and then we give it BK memory property host visible bit and BK memory property host coherent bit, which was, where is it? Can be used as source in memory transfer operations because it can be used as destination, so that's the intent. and then device local. The memory has and it's usually not accessible by the CPU. Yeah, I already know that. What is happening to the site? Let's go. Yeah, so excited. I can't find the... create buffer. Property host visible bit. Buffer usage destination bit. Buffer usage vertex bit. BK memory property device local. Oh, I see. Device local, host coherent. Okay. I didn't see that. So we create the buffer, then we copy the memory to the one that is on the CPU. Then we create the second buffer, that is the destination one. Which is on the GPU. We use this, which is records the command buffer and then executes it, and we wait on idle. Which under the hood it grabs staging buffer and render vertex buffer. Yeah, and we copy data to the staging buffer memory. Good. Then we finally do that, and then we just free both of the resources, and that's it. Okay. Anything else? You can implement an allocator yourself. Yeah, we already read that. Index buffer. Okay, so this is the same as OpenGL. The 3D meshes you'll be rendering in a real-world application will often share vertices between multiple triangles. This already happens even with something simple like drawing a rectangle. Yeah, BO, B1, B3, B2, and here we have to specify. So this is 4 and this is 5, 6. Drawing rectangles takes 2 triangles, which means we need vertex buffer with 6 vertices. The problem is that the data of 2 vertices needs to be duplicated, resulting in 50% redundancy. It only gets worse with more complex meshes where vertices are reused in an average number of 3 triangles. The solution to this problem is to use an index buffer. An index buffer is essentially an array of pointers into the vertex buffer. It allows you to reorder the vertex data and reuse existing data for multiple vertices. The illustration above demonstrates what the index buffer would look like for the rectangle and whatever. So instead of having to do all of that for a quad, we can just do this for coordinates. Here it is. I forgot I have to. I should probably. No. Can I. If I do this, what happens? Okay, that works. Fuck. There you go. Are you using CGLM for your math library? Yes. And these are the indices. 0, 1, 2, 2, 3, 0. It is possible to use either UN16 or UN32 for your index buffer depending on the number of entries in vertices. We can stick to UN16 for now because we are using less than unique vertices. Just like the vertex data, the indices need to be uploaded into a BK buffer for the GPU to be able to access them. Define 2 new class members to hold the resources for the index buffer. Vertex buffer, here it is. Okay. I am alt-tabbing, but I should unmap alt-tab, so I stop using it. Because that's what my window manager is for. The create index buffer function will add, now is almost identical to create vertex buffer, except for index buffer bit, that. Yeah. Create vertex buffer. This is size of indices. And then create that, render that. And then here no and no. This is data directly and those are capitalized. What window manager are you using? Como Ready. Oh, there we go. This one. It's pretty easy to set up. And I think you can make it open certain tabs whenever you, like if you press Alt 3, it opens always any of them. When you press Alt 1, it opens always this. Alt 2 always opens Discord, for example. Something like that, but I'm not sure how you do it. It's not the best for some programs like Photoshop. It doesn't detect it as a window. But apart from that, it's pretty good. But that's like Windows. It's hard that everything works well in terms of Windows. There's so many window managers these days. I've never heard of this one. I thought this was the most famous one on Windows. It looked like the most stable one. I don't really care about looks. I just wanted the one that worked the best. If you have a better one, tell me about it. Like the older, probably the better. What, this is Windows? Yeah, it is Windows. It is Windows. Doesn't look like so. There are only two notable differences. The buffer size is now equal to the number of indices times the size of the index type, either UN16 or UN32. The usage of index buffer should be, yeah, instead of vertex bit, that's what we said, which makes sense. What's up? You can limit it. You know how to do it? Okay. Other than that, the process is exactly the same. We create a staging buffer to copy the contents of indices to, and then copy it to the final device local index buffer. The index buffer should be cleaned up at the end of the program, like the vertex buffer. Okay, first of all, I should init Vulkan, and where is this vertex buffer? Index buffer, and we need to, nope, oh, I didn't name it like that, and then we need to add it in here, create vertex buffer, add it on here, fixes that, and it's executed after vertex buffer. Yeah, I mean, I don't think it will do anything. Not gonna lie, it looks pretty nice for Windows. Yeah, it does. You speak French? I don't. I switched from Linux to WSL recently, and it's giving me the best of both. It even supports X11 forwarding nowadays. Yeah, you can open many graphical interfaces with it. Thank you for these streams. I am currently a beginner in C and I'm learning. No worries. I was, well, I am a beginner still. Just a bit less of a beginner. Vertex buffer if vendor dot index buffer doesn't equal no, then we though about WSL, like, it's great, but running NeoVim on Windows, it's such a pain on the ass. Like, there's always something going wrong, like some plugin not working because they assume that you're using Linux, or the graphical interface going like really slow. This is why I use Neobyte, because it supports 144 FPS, as well as like all terminals for Windows are very bad, even Alacrity, like they're very slow. And then you don't really have many options for this. Like, I use MinGW, before I used git bash. I'm not sure. And running NeoVim on the OSL feels pretty bad. At least in my case, it didn't feel good. Felt pretty slow. Running Doom Emacs on the OSL on Windows, you're not alone. It's such a pain to set up. Yeah. I mean, not that long ago, I was thinking on switching to Emacs because it was so painful to use NeoVim without it being like laggy, and have a beefy PC, right? I have a really good PC. There's no way an editor runs badly, you know? So it's either that or switch to Linux. But I wanted to do graphics programming, and Windows is usually the place to do that. Until I found Neobyte, and that fixed it for me. Most tools are Linux only, yeah. That's also the problem. But a fair amount, like if you're using MinGW, you can get GCC working on Windows. Or Clang with MSVC. For beginners, should I try Vim? I'm not sure. I mean, if you're already decent at coding in like one language, and you don't have to focus on syntax and whatever, and you can just write code, yeah, go ahead, learn Vim. But you need to be able to write only using your fingers in the homebrew. Like, you need to know touch typing. If you don't, then it's for nothing, right? Because you're gonna be looking at your keyboard to see what Vim bindings you have to use. So not very useful. First, learn touch typing if you don't know it, and then learn NeoVim or Vim, whatever. Use something that doesn't make you hate programming. Oh yeah. Pretty beefy. I use SDL for the platform layer, so I don't have to worry about cross-platform capability. Use Linux Mint. Cool. Yeah, I use SDL too, SDL3 in my case, but it's the same thing. Documentation is pretty scarce on that though. I find nothing sometimes. Like no examples, nothing. It's usually old SDL code. Or some random repo using SDL3. Using an index buffer for drawing involves 2 changes to record command buffer. By the way, after creating it, nothing should happen, right? Like it should be the same thing. It shouldn't have any error. It's just unused memory. Yeah. We need to bind the index buffer, just like we did for the vertex buffer. The difference is that you can only use a single index buffer. It's unfortunately not possible to use different indices for each vertex attribute, so we do still have to completely duplicate vertex data, even if just one attribute varies. Right. So bind vertex buffers and bind index buffer. Bind, oh, this is on record. Bind vertex buffers. Do I have to do this? Right, because there's only one buffer, right? Yeah, and here you can have multiple. Gotcha. If I remember correctly, SDL3 has the GPU API. Yep. It looks pretty neat. I was thinking of abstracting my Vulkan implementation to something like that to support multiple APIs. Because like just enough abstraction for it to not be like a really high level API and not a really low level API like Vulkan. Have you explored it? Yeah, I mean I've read a lot of code and written a triangle on it. It's like 100 lines of code. Wait, I even have it here. Here it is. 134. But it looks kind of ugly. You create the window, create the GPU device like Vulkan, vertex buffer, transfer buffer, vertex shader, fragment shader. You know, it's like Vulkan pretty much, but a lot less verbose. So you bind it, which has the index buffer bytes offset of it, we are 0, and the type of index data as parameters. As mentioned before, the possible types are BK index type uint16 and uint32. Just binding an index buffer doesn't change anything yet. We need to change the drawing command to tell Vulkan that we use that we need to use the index buffer. BK command draw and replace it with BK command draw indexed. BK draw, BK command draw here. And this is U32. Oh, I need to get the size of this. And then divided by size of indices 0. And yeah. By the way, I like to do begin render pass here. You begin the render pass and you end it. And it's all in a block. At least it's not 1,000 lines for a triangle. Oh yeah. I think Raylib has experimental Vulkan support. Oh, that's interesting. The problem about Vulkan it's too abstracted, like very much abstracted, which is fine for 2D, but then for 3D it starts getting a bit difficult. And like at that point you could just use normal OpenGL, I feel like. But then if it uses Vulkan, then it gets a little bit more interesting. Though it's still too abstracted, I think it would get on the way. And I should try to execute this. Oops. I said because I didn't save this. What? Okay, definitely something wrong. Probably in record, command buffers. So what does this need? Index count. Am I doing this wrong? It's 4, right? 4? Like what happens if I just do that? No, okay. So I'm binding it. Wait. Okay, there we go. I'm binding it. Okay, maybe I can't do this. No, not either. I mean, they do it normally, right? bk bind index buffer and bk command bind index buffer. It is uint16. Right. Then this is the same as theirs. These are our indices. This is u16. Then we upload the index buffer. This is just the size, which we were getting before by the same way. Buffer size, buffer size. What?
How much should I limit?
Just 50%. So 100. Wait.
That's kilobytes, by the way.
Okay, I don't know, calculate it. Like 10,000. Thoughts on Vulkan so far? It's very explicit, which I like. It's not as hard as they make it. It's just a bunch of struct initialization. Like you have to create so many structs for doing anything. But that's it. I mean, I understand that it feels good. Just a bit verbose in that part. But I think you can abstract a lot of things very easily. It's the initialization that is verbose, but apart from that, like, then you just have to recreate your pipeline and, you know, create your vertex buffers and whatever. But then it's not as verbose after that. It's the initial part. Right, so indices should be like you set 6. Let's try setting 6. CI 6. Yeah, not either. You say that now, just wait until you have to multi-thread it and use the compute shader. Right, I mean, if you want to multi-thread it, then it's like another level of complexity, but then you can also cache pipelines and whatever, right? So you can just not multi-thread it, and like if you really need to, then just multi-thread. I mean, the reality is you can make it as complex as you want, and you can make it as simple as you want as well. It goes both ways. By the way, where do I have my other to do? Yeah, this is good. That's true, yeah. So we are using index buffer here. I mean, I don't know, what changes? We do size off instead of this. We create the staging buffer like before. Yeah. Transfer the SRC bit. And we just do it on host. Then we map this, give it data, use indices, give it buffer size and staging memory, and then buffer size, destination bit index buffer, copy the buffer, and then we destroy the buffer and free the memory, right? And then in here it's the same thing, and in here it's the same thing, maybe like this. I mean, I don't think it's gonna be that, but we can try it. Nope. We are freeing it at the end, and we bind it like that normally. And I removed the command draw, right? Yeah, and now it's indexed. And it uses the size of that, 1, which is the instance count. First index is at 0, offset at 0, first instance at 0. Does my shader do anything weird? It just takes the position, color, and draws whatever position it has to draw, so that's normal. I don't know, let's look at their code, maybe they did something weird. Newest 3 months ago. I was having problems with this. Did you recompile the shader? Yeah, it's recompiled in each render. I wonder how concurrency would fare in Vulkan. What do you mean? I also didn't edit the shaders. By the way, look how they are compiled. This is on the build script in C, method.h plug. Anyways. So where do we have indices? No. What did he name them? Yeah. Indices. It's the same thing we have. 0, 1, 2, 2, 3, 0. And that is that. Oh, look at that. I was setting old values, it seems. I'm not sure what happened there. Oh god. Okay, there we go. Yeah. Keep it up, dude. Love the dedication. Thank you. The concurrency they use for networking, but it could be a stupid idea. I still don't know what you mean, like, you wonder how would it work? Well, anyways, that is done. Yeah, I knew it had something to do with vertices. Is he talking about multiplayer games, maybe? Mm. Conclusion. There's no conclusion. Now you run your program and you get this. You now know how to save memory by reusing vertices with index buffers. This will become especially important in a future chapter where we're going to load complex 3D models. Right. The previous chapter already mentioned that you should allocate multiple resources like buffers from a single memory allocation, but in fact you should go do a you should go a step further. Dyslexias. Vulkan memory management. Java developers recommend that you also store multiple buffers like vertex and index buffer into a single BK buffer and use offsets in commands like bk bind vertex buffers. The advantage is that your data is more cache friendly in that case because it's closer together. It is even possible to reuse the same chunk of memory for multiple resources if they are not used during the same render operations, provided that their data is refreshed, of course. This is also known as aliasing, and some Vulkan functions have explicit flags to specify that you want to do this. That's too tryhard, but I get the you're reusing the same chunk. Wait, yeah, adding offsets for it. How do you do it? Create buffer. So you create one buffer with the size of both of those. It'll be this plus and the index buffer size. Then you map both, but the thing is, oh right, because then you can create the, no, I still don't get it. Do they mean staging buffer only, or because you would still need to create a vertex and index buffer? It's an optimization technique, yeah. But I'm wondering, like, how does it work? Because when you create buffer, you give it the usage flag, which destination bit and vertex buffer bit. Can you also give it index buffer bit? You should commit the code first before trying it. It will be a pain to debug later. No, I was not going to try it. I just wanted to know how it works. Actually, let's just ask ChatGPT how it works. Here they say you can reuse the same buffer and then just use index offsets. How would you do this? Do they mean use the same staging buffer or also the same vertex / index buffer, since they have a, what was the name? Usage flag. Usage flag. And depending on if it is a vertex buffer or index buffer, it changes. So can you reuse it anyways? Yeah, that's what I'm thinking. I'm just not sure how would you do it. Your final GPU side buffer, not just a staging buffer, right? So, oh, they add the 2 bits. Okay, I thought it was not possible. So then you grab both sizes, create the buffer, map the memory, and then when you're binding, you have to save the offset. Okay, makes sense. I like doing this whenever I don't understand a concept, I just give it to ChatGPT, they implement it, explain it, and that's it. I don't use any code that it gives me. I just try to understand the concept. I think it's like the best way to use AI. You can use bitwise or operator some of the flags, yeah. I mean, it just sets all of the bits for the different flags. Okay, descriptor, layout, and buffer. These are like SSPOs? Oh no, just normal UBOs. Okay. We're now able to pass arbitrary attributes to the vertex shader for each buffer, for each vertex, but what about global variables? We're going to move on to the 3D graphics from this chapter on, and that requires a model view projection matrix. We could include it as vertex data, but it's a waste of memory and it would require us to update the vertex buffer whenever the transformation changes. The transformation could easily change every single frame. The right way to tackle this in Vulkan is to use resource descriptors. A descriptor is a way for shaders to freely access resources like buffers and images. We are going to set up a buffer that contains the transformation matrices and have the vertex shader access them through a descriptor. Usage of descriptors consists of 3 parts. Specifies descriptor layout during pipeline creation. Allocate descriptor set from a descriptor pool. Bind descriptor set during rendering. I imagine that, so you just need to give the layout on the pipeline with strides and whatever. The descriptor layout specifies the type of resources that are going to be accessed by the pipeline, just like a render pass specifies the types of attachments that will be accessed. The descriptor set specifies the actual buffer or image resources that will be bound to the descriptors. Like a frame buffer specifies the descriptor is then bound for the drawing comments, just like the vertex buffers and frame buffers that would be on the when we record comments. By the way, this part is quite long. You can only see the result in the next part. Is it? There are many types of descriptors, but in this chapter we'll work with uniform buffer objects, UBOs. We'll look at other types of descriptors in the future chapters, but the basic process is the same. Let's say we have the data we want the vertex shader to have in a sysstruct like this. Okay, MVP. So how do I mat4s? Yeah. I hate this, by the way. And MVP UBO maybe. let's just keep it like this. Then we can copy the data to a BK buffer and access it through a uniform object descriptor from the vertex shader like this. Okay. So vert. So instead of position and in color, oh right. Since it's an uniform, I think it doesn't matter. Right, because binding 0. Yeah. Okay. What is that? Why is it? I think you can create this struct. Oh no, never mind. It doesn't work for UBOs. That's just for SSPOs. Then you do all of this. Multiply MVP. UBO projection, UBO view, UBO model, in position 0. Okay. We're going to update the model, view, and projection matrices every frame to make the rectangle from the previous chapter spin around in 3D. Or we can just use an actual square. Modify the vertex shader to include the uniform buffer object like it was specified above. I will assume that you're familiar with MVP transformations if you're not the resource mentioned in the first chapter. What is this? Oh. Yeah. So that. Note that the order of uniform in and out declarations doesn't matter. Yeah, that's what I thought. The binding directive is similar to the location directive for attributes. We're going to reference this binding in the descriptor layout. The line with GL position is changed to use the transformations to compute the final position and clip coordinates, unlike the 2D triangles. The last component of the clip coordinates may not be 1, which will result in division 1 converted to the final normalized device coordinates on the screen. This is used in perspective projection as a perspective division. Okay, whatever. We already know this. The next step is to define the UBOs. Okay, we already have it. We can exactly match the definition in the shader using the types in GLM. The data in the matrix is binary compatible with the way shaders expected. So we can later just mem copy a uniform buffer object to a BK buffer. We need to provide details about every descriptor binding used in the shaders for pipeline creation, just like we had to do with vertex attributes and its location index. We'll set up a new function to define all of this information called create descriptor layout. It should be called right before pipeline creation because we're going to need it in there, of course. So init Vulkan pipeline create UBO. Okay, and create UBO should go right above here. Create index buffer, I'm gonna add it right under. Yeah. Descriptor layout. Oh, that's how they call it. Okay. Descriptor layout. Because maybe it's not related. Okay. Descriptor layout. So every binding needs to be described through a BK descriptor set layout binding struct. What am I doing? Binding 0, yes, BK descriptor type uniform buffer, and then, oh, what types are there? Sampler, storage image. Where's the storage buffer? Yeah, this is what we will use later. The first two fields specify the binding using the shader and the type descriptor, which is a uniform buffer object. It is possible for the shader variable to represent an uniform of array, an array of uniform buffer objects, and descriptor count specifies the number of values in the array. Yeah, this could be used to specify a transformation for each of the bones in a skeleton for skeletal animations, for example. Our MVP transformation is in a single uniform buffer object, so we are using a descriptor count of 1. This is shader stage vertex bit. You didn't specify this on OpenGL. Which shader stages of the descriptor is going to be referenced? The stage flags field can be a combination of BK shader stage flag bits values or the value BK shader stage all graphics. Yeah, this is what happens by default, I think. In our case, we are only referencing the descriptor from the vertex shader. Immutable samplers. Only relevant for image sampling related descriptors which we're going to look at later. You can leave this to its default value. To a single BK descriptor layout object, we define a new class member above pipeline layout. Pipeline layout. Yeah. We can then create it using BK create descriptor set layout. This function accepts a simple BK descriptor set layout create info with the array of bindings. All right. Layout info. There we go. No, and this is render.description set layout. Good. We're gonna grab the error just in case. Result is equal to BK success, else create descriptor layout failed to create descriptor layout with error string BK result bang. We need to specify the descriptor set layout during pipeline creation to tell Vulkan which descriptors the shader will be using. Descriptor set layouts are specified in the pipeline layout object. Modify the BK pipeline layout create info to reference the layout object. Layout create info pipeline layout create info. And we are set layout count 1 and then descriptor set layout. You may wonder why it's possible to specify multiple descriptor set layouts here, because a single one already includes all of the bindings. We'll get back to that in the next chapter, where we'll look into descriptor pools and descriptor sets. The descriptor layout should stick around while we may create new graphics pipelines, for example, until the program ends. Okay. We should do it before the the pipeline layout. F render dot what was the name? Layout, descriptor layout. Okay. In the next chapter, we'll specify the buffer that contains the UBO data for the shader, but we don't need to create this buffer first. We need to create this buffer first. We're going to copy new data to the uniform buffer every frame, so it doesn't really make sense to have a staging buffer. It would just add extra overhead in this case and likely degrade performance instead of improving it. We should have multiple buffers because multiple frames may be in flight at the same time, and we don't want to update the buffer in preparation of the next frame while a previous one is still reading from it. Thus, we need to have as many uniform buffers as we have frames in flight, and write to a uniform buffer that is not currently being read by the GPU. To that end, add a new class member for uniform buffers and uniform buffer memory. Vector void pointer. I don't have one of those. So they added after index buffer memory index. Okay, so this becomes vector device memory and void pointer. Maybe any. So first of all, this buffer, then this bk device memory, and finally this, which is void pointer, which we could edit here since it's part of that. Yeah. Similarly, create a new function, create uniform buffers, that is called after create index buffer and allocates the buffers. We allocate but don't copy, because we have to do it per frame. Create index buffers. Right. Max frames in flight 2. So back reserve max frames in flight. and yes. Then create buffer, render, I mean, we could just do current uniform buffer, yeah, and it is equal to render dot uniform buffers I data, and this would be bk buffer. And same thing with uniform buffers memory, current uniform buffer memory, uniform buffer memory, and this is bk memory. I forgot. I can't. Device memory, right? bk device memory. Did you write your own dynamic array library? Yeah, it's I've had it for a while. Pretty practical. I use it everywhere. Same with my on IO library. I am hello Levasco. I'm finally able to catch a stream and stay. Good. Capacity plus size is equal dynamic array. Yeah. Current uniform buffer memory, and we should actually back at pointer. I hate this autocomplete. I'm so happy. I'm glad you're happy, bro. I'm getting the pointer, so why doesn't it detect it as a pointer? There you go. Render, and then current uniform buffer, and oh wait, what? Current buffer's memory. Oh, uniform buffer memory and current uniform buffer. I'm doing it wrong, I guess. Oh god. Current uniform buffer memory. What? So we need device memory. So it's this. And then at the end we need the data. Which is uniform buffers mapped. Oh, uniform buffers mapped. Gotcha. And this needs to be that. Oh. Yeah, never mind, I guess. I stream too, and something that helps keep people interested is music. If you'd like, I can share the names of some artists. You know, I used to stream with music, but then I would get copyrighted every time, because YouTube does not have like different bot and different, what's the name? Different bot and the stream things. So you can't have two audio channels. unlike in Twitch. So in Twitch I can use music. That's the main reason I don't use it. I mean, I could just stream non-copyrighted music, but then I would have to make a playlist. None of these words are in Star Trek, right? Except the void pointer. Okay, anyways. We create the uniform buffer, create index buffer. They say before or after index. It's called after. I mean, it has no influence, right? But we're gonna do as they say. Create vertex index. Uniform buffers. A stream to YouTube using OBS, it includes both OS playback and my mic. I would have to look into it. If it has support for bots to have the normal audio track and then like the actual stream to have music, then it should do it. Using PK map memory to get a pointer to which we can write the data later on. The buffer stays mapped to this pointer for the application's whole lifetime. This technique is called persisting mapping and works on all Vulkan implementations. Not having to map the buffer every time we need to update it increases performance as mapping is not free. Yeah. The uniform will be used for all draw calls, so the buffer containing it should be destroyed when we stop rendering, which is right above descriptor set layout. I'll just add it here because I'm lazy. And uniform buffers, render data. I gotta go, it's already late. Remember the result in the next part. See ya. Remember the result in next part? I will remember it. I basically make the OS playback in the stream quieter than the mic. Oh yeah, I mean, I get that, right? What I'm trying to say is, in OBS, you can have different audio tracks. So when you upload the bot, so you see that I have the browser on first one, this is for the actual stream, and then the mic on the second one. So when I upload the bot, I only use the second track, which doesn't include the music, and then on the first one I use the track itself with the music. So the stream can listen to the music, but when I upload the bot, it doesn't play. But that's for Twitch only, because YouTube doesn't have it. Then yeah, here I make it a bit quieter. Yeah. But I should probably get like a non-copyrighted list of lo-fi music or whatever, something to have in the background. Updating uniform data, create a new new function, update uniform data. Wait, oh never mind, no, it won't work. And add the code to it from the drawFrame function before submitting the next frame. So this would be right before submitting the next frame. Submit info. Right, so here. And then update uniform buffer. Current frame, which we get from, where is it? Render the current frame. And then that doesn't change. Okay. So index buffer. Hello fellow programmers. Hello, hello. Void update uniform buffer. And it takes current image. Oh, is it current frame or current image? Because this is index, image index. I guess it's current frame and they just named it poorly. An artist that I accidentally got my mom hooked in is Mikel. He's really good. Zelda and Chill album as well as second and third ones. That has some nice chill music. I wonder if his music would strike you. Yeah, I mean any independent artist usually copyright strikes. Well, not strikes, but they just don't let you monetize. Nintendo Music does not copyright, which is interesting. What is chrono? Exposes functions to precise timekeeping. We'll use this to make sure that the geometry rotates 90 degrees per second regardless of frame rate. Oh, I mean, we have delta time. Yeah. Start time and current time. And then it just gets the difference between both. We'll now define the model, view, and projection transformations in the uniform buffer object. The model rotation will be a simple rotation around the z-axis using the time variable. We can actually make it a bit more interesting. Update. So this is 0, this is GLMS rotate GLM, what is it? GLM identity, mat4 identity. Okay, something like that. I'll add it here. mat4 identity matrix. GLM. Okay, let's try this. That's it. No, but I want S. So I guess I have to do GLMS. Yeah. Okay, so I can give it this now. I guess mat for rotate. Mat for S rotate. Mat for rotate. GLMS. Mat for rotate. Or I guess just rotate. Yeah, could be. The thing is, I don't know what it returns, and I can't jump into it. Okay, whatever. This is GLM rad multiplied by time. Right. So you're forgetting to use the strict prototypes void when empty function. Yeah, I mean, I could. I just find it too verbose. I was doing it on my like other public code bases, but since this is not public, I don't really care. I'm a beginner, but are you doing this in C or C++? On C23. By the way, I think you don't have to do the void prototype on C23. Is that correct? Yeah. In C17 and earlier versions, the standard does not provide a prototype for main. Otherwise, in C23, main does provide a prototype for main and is fully equivalent except for spelling to whatever. So it's not necessary as far as I'm aware. GLMS spec 3. Right, it does. Okay, I'll have to just copy my CPU render code. Without strict prototypes, you can specify arguments when calling it. Yep, but if you have an LSP, you wouldn't make that error, right? I'll just copy this. Yeah, it's black 4S. I'll add it on the renderer. I do that, and do I do anything else special? No. And what do I do for current time? GLMS, rotate, okay. Current time is SDL get ticks. Alright, so time would be this, oh wait, didn't copy it. Why wouldn't I use F64, huh? And then they divide that by 24. Yeah, I mean, I guess that's what I want to do. Sorta. Back. Wait, what is this? Current time. Yeah, never mind. And then here, back 3 create. Oh, I'm using current frame. I'm stuck with current time. Okay, then the view is this. Which we don't have. GLMS doesn't have GLMS look at. CGLM look at. Where's the documentation here? Look at. Yeah. Right, it's just that the naming is a bit weird. Back 3 create. Back 3 create and back 3 create. Honestly, the the documentation from, well, the quality of CGLM is so much better than normal GLM. For the view transformations, I've decided to look at the geometry from above 45-degree angle. Takes the eye position, center position, well, whatever, I already know this. Rad and swap chain extent, so this F32. I like 60 degrees. Oops. And where's the model? They just rotated. I'd like to rotate it around that. This is gonna be the craziest Windows rise. Yeah. This is the best Windows setup you can get. It is important to use the current swap chain extent to calculate the expert, yeah, whatever. And then they do this weird thing where the y coordinate of the clip coordinates is inverted. The easiest way to compensate this is to flip the sign. Oh, damn, I didn't know that was a thing in OpenGL. Makes sense. If you don't do this, then the image will be rendered upside down. Yeah, I was getting this on SDL. Now the thing is, can I access this raw? Oh yeah. I hecky want to do this. Do you have your stuff in GitHub? I do. UVM config is here. And then the window manager, I don't have it, but the configuration is very simple anyways. You could do it in like 1 hour. And I do it from Como Revi window manager. If you want to try it out, I also send the link. By the way, if you're making this a CLI application that can take flags and arguments, I made a robust single header library for argument parsing and automatic usage generation when help is specified. It is C23 and embedded friendly. I have my own CLI parser too. Thanks for for the self-promo. Where the y coordinate of the clip coordinates is inverted, blah blah blah. If you don't do this, then the image will be rendered upside down. All of the transformations are defined now, so we can copy the data in the uniform buffer object to the current uniform buffer. This happens in exactly the same way as we did it for the vertex buffers, except without a staging buffer. As noted earlier, we only map the uniform buffer once, so we can directly write to it without having to map again. Makes sense? Render, and then we are using current frame because current image does not make sense, and of course data. You give the UBO and the size of the UBO. This looks so bad if I don't. Yeah, that's better. Thank you so much, no worries. Of course you do, you literally have your own build system too. You use CMake like a simpleton. Method.h is so simple. Like if you already know CMake, then you can learn method.h in like 30 minutes. Or just look at this first example and already have something working. Like this is the entire build script, and it compiles my shaders even. So yeah. If you need any help, you can join the Discord and send your build script or whatever. It's the equivalent of CMake. Either me or someone else will help you. Using a UBO this way is not the most efficient way to pass frequently changing values to the shader, of course, because we're getting this type of memory again. A more efficient way to pass a small buffer of data to shaders are push constants. We may look at this in a future chapter. In the next chapter, we'll look at descriptor sets, which will actually bind the BK buffers to uniform buffer descriptors so that the shader can access the transformation data. Yeah, because we are just mapping, we need to... Discord link? I think it's in the description. Let me check. I'm pretty sure I added it. Yeah, it's here. By the way, I'm gonna take a quick break and get water and take a bathroom break. Let me add a message. Bathroom break. Select font, comic, mono, of course. Select color. This, and there was a yeah. No, not this. Left. Oh, just that. How can I center it? Center to screen, yeah. There you go. Be right back. Okay, I'm back. The text is yellow, holy crap, the text is yellow. Okay. So that's it. What else do we have? So this is the update, which we are already we're not calling, of course, because we haven't defined it. Okay, and we are already creating the descriptor layout. And then this same descriptor layout, we are using it on here. So the pipeline knows about it. We are already updating it. We are creating it. Wait, no, we are creating the uniform buffers. Here, we create the buffers for each frame in flight and we map the memory. And we are using host visible bit. So these are all staging buffers, sort of, not sort of. We use usage uniform and host coherent bit. We have a link for the Discord. Oh wait, description. Yeah, it is in the description. Once it is mapped, we can mem copy. But when do we unmap it? That's the interesting part. It also said using a UBO this way is not the most efficient way to frequently. Right, we need to add push constants, which we'll do later on. We'll look at descriptor sets, which will actually bind the BK buffers to the uniform buffer descriptor so that the shader can access this information data. Alright. Had fun watching the stream, see ya. Okay. The descriptor layout from the previous chapter describes this type of descriptors that can be bound. In this chapter, we're going to create a descriptor set for each BK buffer resource to bind it to the uniform buffer descriptor. Descriptor pool. Descriptor sets can't be created directly. They must be allocated from a pool like command buffers. The equivalent for descriptor sets is unsurprisingly called descriptor pool. We'll write a new function, create descriptor 2 to set it up, which is done right after create uniform buffers. Uniform buffers. Wait, create descriptor pool. We are going to add it, and we are going to init Vulkan. Create descriptor. Wait, where is it? Uniform buffers here. Wait. Create descriptor pool. create uniform buffers. Yeah, and then create descriptor pool. Okay. And here we need to describe which we first need to describe which descriptor types our descriptor sets are going to contain and how many of them using BK descriptor pool size structures. So it's always the same as max frames in flight. U32. I mean, we need that. We'll allocate one of these descriptors for every frame. This pool size structure is referenced by the main BK descriptor pool create info. Interesting. Oh, I thought it was the command pool. Dumb. So it's nothing new. We just reference the pool size. Yeah. Aside from the maximum number of individual descriptors that are available, we'll also need to specify the maximum number of descriptor sets that will be allocated, which again, it's our handy at U32. This structure has an optional flag similar to command pools that determines if individual descriptor sets can be freed or not. BK descriptor pool create free descriptor set bit. We're not going to touch the descriptor set after creating it, so we don't need this flag. You can leave flags to its default value of 0. Well, so the entire thing is 0. We can add this right on here, descriptor pool, and we just create it. BK result. What? BK result assert result is equal to BK success. If so, create descriptor pool failed to create descriptor pool with error. String BK result. Good. Add a new class member to store, descriptor set. We can now look at descriptor sets themselves, add a descriptor sets function for that purpose. So basically, you create the descriptor pool and then you need to create the descriptor sets. And from there you can set it. And again, I guess we are going to create our 3 max frames in flight. The descriptor set allocation is described with a BK descriptor set allocate info struct. You need to specify the descriptor pool to allocate from, the number of descriptor sets to allocate, and the descriptor layout to base them on. This is BK descriptor. Oh, we don't have this? layouts is equal to this. No, we don't. Okay, I'm gonna create the vector. I mean, of course, we don't have it. I gotta go, I might be back. This was fun, reminds me of my own streams a lot. So yeah, have a good one. And layouts.data, yep. Now the thing is, they set this with descriptor set layout. Descriptor set layout vendor. Right, so we set only one value, right? Because that's all we have. Back reserve layouts and max frames in flight. Yeah, and then we just back push. Layouts that. Though okay, I wonder what is gonna happen. Now we can just play it safe and do data 0 is equal to this. Yeah. Oh, with the same layout? Oh, right. So I need to push it 3 times. Well, then that would have been easier. Size t I is equal to 0, I is less than max frames in flight, and then a plus plus. That makes no sense, by the way. Yeah, because no, C++ is weird. Hello, Lon CZ. How's it going? Allocate info, descriptor pool, max frames in flight, layout data, and then we can create them. In our case, we'll create one descriptor set for each frame in flight with the same layout. Unfortunately, we need all the copies of the layout because the next function expects an array matching the number of sets. Add a class member to hold the descriptor set handles and allocate them with bk allocate descriptor sets. What system do you use? Like operating system? Fine, all good, all good.